Hello everyone, my name is Rohit and I am here to explain the topic Irreducible M Matrices. Coming to the introduction part, the name M matrix was seemingly originally chosen by Alexander Ostrowski in reference to the Hermann Minkowski, who proved that if a Z matrix has all of its row sums positive, then the determinant of that matrix is positive. Definition: an M matrix is a Z matrix with eigenvalues whose real parts are non-negative. Z matrix is the matrix whose half-diagonal entries are less than or equals to 0. That is, matrix of the form Z equals to Zij. Zij less than or equals to 0. That is, I not equals to J. The set of non-singular M matrices are a subset of the class of P matrices and also the class of inverse positive matrices, that is, matrices with inverse belonging to the class of positive matrices. M matrices can be expressed as alpha into I minus P for some non-negative matrix P and real alpha greater than 0. A matrix A is irreducible if there does not exist a permutation matrix P such that P transpose into A into P equals to B, C, 0, D. There are many definitions for irreducibility of a matrix. Characterizations. Let A be n into n real Z matrix, that is A equals to Aij, where Aij less than or equals to 0 for all I not equals to j, 1 less than or equals to I, comma j less than or equals to n. Then matrix A is also an M matrix if it can be expressed in the form A equals to Si minus B, where B equals to Bij with Bij greater than or equals to 0 for all 1 less than or equals to I, comma j less than or equals to n, where S is at least as large as the maximum of the moduli of the eigenvalues of B, and I is an identity matrix. For the non-singularity of A, according to the Perron-Frobenius theorem, it must be the case that shown here. Also, for a non-singular M matrix, the diagonal elements Aii of A must be positive. Here we will further characterize only the class of non-singular M matrices. Many statements that are equivalent to this definition of non-singular M matrices are known, and any one of these statements can serve as a starting definition of a non-singular M matrix. For example, Plemons lists 40 such equivalences. These characterizations has been categorized by Plemons in terms of their relations to the properties of: first point, positivity of a principal minors; second one, inverse positivity and splittings; third, stability; and fourth, semi-positivity and diagonal dominance. Coming to the first point, positivity of a principal minors. All the principal minors of A are positive, that is, the determinant of each submatrix of A obtained by deleting a set, possibly empty, of corresponding rows and columns of A is positive. A plus D is non-singular for each non-negative diagonal matrix D. Every real eigenvalue of A is positive. All the leading principal minors of A are positive. There exist lower and upper triangular matrices L and U respectively with positive diagonals such that A equals to LU. Second one, inverse positivity and splittings. A is inverse positive, that is, A inverse exists and A inverse greater than equals to 0. A is monotone, that is, Ax greater than or equals to 0 implies x greater than or equals to 0. A has a convergent regular splitting, that is, A has a representation A equals to m minus n, where m inverse should be greater than or equals to 0, comma n should be greater than or equals to 0 with m inverse into n convergent. There exist inverse positive matrices m1 and m2 with m1 less than or equals to A less than or equals to m2. Every regular splitting of A is convergent. Third point, stability. There exists a positive diagonal matrix D such that A into D plus D into A transpose is positive definite. A is positive stable. That is, the real part of each eigenvalue of A is positive. There exists a symmetric positive definite matrix W such that A into W plus W into A transpose is positive definite. A plus I is non-singular and G equals to A plus I whole inverse into A minus I is convergent. A plus I is non-singular and for G equals to A plus I whole inverse into A minus I. There exists a positive definite symmetric matrix W such that W minus G transpose into W into G is positive definite. Fourth point, semi-positivity and diagonal dominance. A is a semi-positive, that is, there exists x greater than 0 with ax greater than 0. There exists x greater than or equals to 0 with ax greater than 0. There exists a positive diagonal matrix D such that A into D has all positive row sums. A has all positive diagonal elements and there exists a positive diagonal matrix D such that AD is strictly diagonally dominant. A has all positive diagonal elements and there exists a positive diagonal matrix D such that D inverse into A into D is strictly diagonally dominant. If and only if there exists a permutation matrix P and an integer k belongs to 1 comma so on up to n minus 1 such that P into A into P transpose equals to A11, A12, 0, A22, where A11 is of the order k into k and A22 is of the order n minus k into n minus k. If A is not reducible, then A is said to be irreducible. An irreducible matrix is not similar to a block upper triangular matrix via permutation matrices. That is, if M is reducible, then P into M into P transpose equals to X, Y, 0, Z. For some permutations matrix P and submatrices blocks X, Y, Z. Any matrix that lacks 0 entries is thus irreducible because no permutations can create a 0 when none existed before, like this 1, 2, 3, 4, 5, 6, 7, 8, 9. In this is an example. A common theorem is that a matrix, that is a matrix M, is irreducible if the corresponding directed graph is strongly connected. We form the graph by using M as an adjacency matrix. So if we take a graph like that is strongly connected, then the adjacency matrix is reducible. It is irreducible for any non-zero values we want to substitute in for ones. Coming to examples, given matrix A equals to 1 0 0 2 3 4 5 6 7 and we know that this is the identity matrix. Next, P equals to 0 0 1 1 0 1 0 1 0 0 and solving P into B into P transpose we get 7 6 5 4 3 2 0 0 1 and this is in the form of P into A into P transpose, that is equals to A11, A12, 0, A22, where A11 is equals to 7, 6, 4, 3, A12 equals to 5 and A22 equals to 1. Coming to second example, B equals to 1, 2, 0, 0, 3, 4, 5, 6, 7. And here P2 equals to 0 0 1 1 0 0 0 1 0. Solving P2 into B into P2 whole transpose equals to, we get 7 5 6 0 1 2 4 0 3. This is not in the form of P into A into P transpose. And thank you.